Greetings, everybody. On this video, we're going to discuss a new tool that we have developed for analyzing and studying chaotic systems, which is called the mean value diagram. Okay, it's very easy to compute. I'm going to put a link to the paper in the description and a link for the MATLAB code in the description as well. Let's explain a little bit the problem. This comes from a recent publication that we had. It was on the Journal of Symmetry. It's called Chaotic Maps with Tunable Mean Value, Application to a UAP Surveillance Mission. Now, the application I'm going to discuss in a separate video, but let's talk about the modeling part. Our problem here was that we wanted to create a family of chaotic maps where it could be possible to control the statistical properties of the maps. Okay, that's why we say with tunable mean value. Let me tell you about this. In many applications of chaos, the statistical properties of the chaotic system matters a lot. So, for example, in chaotic path planning, in chaotic surveillance, in chaotic random bit generators, in chaotic encryption, and possibly in chaotic optimization as well, the statistical behavior of a chaotic time series will affect how the application works, will affect the whole process, right? So a problem comes here that, can we manage to create families of chaotic systems that showcase chaotic behavior? Obviously, we want that. But also, if we are able to control the statistical behavior of the map. So, for example, if we obtain a time series that is chaotic, can this time series be uniform, have a uniform distribution? Can it have a left skewed distribution? Can it have a right skewed distribution? Can we achieve that? So this is a very interesting problem, obviously, from a mathematical and modeling perspective, that we manage to create chaotic systems with controllable statistical properties. But also, it matters a lot from an application perspective as well, because the statistical behavior affects many different applications of chaos. So let me tell you how we did that. We proposed a very general family of piecewise maps with three controllable parameters. I'm giving you an example here. This is a very well-known tent map, but we have generalized the tent map to a much more bigger family, where we basically have three control parameters. And these control parameters are A, B, and C, as you see in the phase diagram here. So A practically controls the interpolation point on the left part of the piecewise maps function. Okay, so it controls the mapping of the interpolation on this part of the curve. So practically, we can move it up and down right here. The parameter B controls the interpolation on the middle point of this curve. So we can move B left and right here. And C controls the right part of the curve. So it moves up and down right here. So the family of maps is piecewise. So we have two subfunctions. They don't have to be linear. This is just an example of the generalized version of the tent map. But in the paper, we have actually proposed a couple more maps as well. So the idea is that by tuning the interpolation points A, B, and C, we can control the final mean value, or if you like, statistical behavior of the resulting time series. And this is very easy to do. Practically, I'm giving you some examples right here. It's a very geometric approach, so it's a very natural approach. And think about it, you know how phase diagrams work and how cobweb diagrams work. The idea is that by changing the mapping interval of each subfunction, you can affect where the mapping will be denser and where it will be less dense. Okay. So for example, by moving A right here higher, we know that the left part of the function is going to map on this interval from 0.4 to 1. So this part will be denser. And again, moving beta on the right, you know that a very larger part of the mapping interval will end up being mapped towards 0.4 until 1. So by tuning these parameters right here, we can very easily and very directly, if you like, affect the mapping interval and bring higher density to specific regions. And you can see, for examples right here, from the classic map, we have a uniform histogram. But when we begin skewing the parameters, we can obtain, as you see right here, for example, a right skewed histogram, as you see, because we have more and more values being mapped on the interval from 0.4 up until 1. Okay. And the same happens with C parameter, but C can affect the whole mapping interval. So instead, we decided to keep C equal to 0. Okay. So this is the idea for the modeling process. to create maps that can achieve this behavior. And you can see right here in this graph that we managed to do that. So now what we wanted to do is develop a numerical tool that we can observe this behavior in the whole parameter interval. So we did that, but let me show you one more example. Here I have only 4 histograms, but let me show you a little bit more. I'm giving you an example where I have C fixed to 0, as I mentioned, A fixed to 0.3, and I'm simply increasing beta. And you will see that we have indeed managed to achieve this control of statistical properties of the time series. We start by having a uniform time series, which is chaotic, of course, to having a right skewed, histogram, which again is from a chaotic time series. So you see how it is beginning to skew on the right little by little by little until it becomes, very, very significantly right skewed, as you see, for higher values of parameter beta. Okay, so we achieved that. And then we created a tool to show this visually. So what we did, first of all, we had for the parameter values of interest, which is A and B from 0 to 1, we computed the range of Lyapunov exponent for each parameter pair. So what you see here is the two-dimensional Lyapunov exponent diagram. Basically, it shows us for each parameter values what is the resulting Lyapunov exponent of the system. So for example, these black regions right here indicate that we have periodic behavior. So I don't care about the periodic behaviors. I will discard these areas completely. While for all of this area right here, we have a positive Lyapunov exponent, which indicates a chaotic behavior. And you can see that in the middle part right here, the Lyapunov exponent is a bit higher. So this is why it is color-coded. So this region here has a higher chaotic behavior, right? So after we did that, we computed the two-dimensional Lyapunov exponent diagram. We took all of these values that correspond to chaotic behavior, and for these values, we computed the mean value of the time series. So we had a very large, for each parameter pair, we computed a very large time series, let's say 10,000 iterations or more. And for each time series, we computed its mean value, but only for the chaotic case, right? So we completely discarded the non-chaotic cases because we don't care about that. We only care about the chaotic behavior. So we obtained this diagram and we termed this the mean value diagram, which is a very useful tool, a very visual tool, gives us a lot of information about the statistical behavior of the system. So first of all, we have a very big range of chaotic behavior, so we have robust chaos. And you can see that for lower values of parameters A and B, the graph here is on the deeper blue color scale, which means that the mean value is around 0.5. Now, considering the fact that the time series maps from 0 to 1 and the mean value is 0.5, you can understand that around these regions we have a uniform histogram. But as the parameter beta increases, the color becomes lighter and lighter, it becomes yellow at the end. So for higher values of the parameter beta, you can see that the mean value is close to 0.8, 0.9. So obviously, the histogram starts by being uniform and ends up being right skewed. Right? So this is what the mean value diagram visually represents. Okay, let's see it actually in a simulation. So the previous GIF that I showed you, where I have a parameter beta increasing, says fixed to 0, as I said, and A equals 0.3. So I'm here on A, 0.3, I'm around here, and beta increases. So we have this transition from here up until 1. So this part of the graph that becomes, starts from deep blue and starts becoming lighter and lighter is illustrated by this fact. We have a uniform histogram, and little by little, the histogram starts becoming non-uniform, and it becomes right skewed at the end. So this is the mean value diagram. I believe it will be extremely useful in studying chaotic systems because it can give us a lot of information about the statistical behavior of any system at hand. Okay, we need to have at least 2 parameters, of course, but this is very common. And, it is very interesting both from a mathematical and modeling perspective, but it will be also very interesting from an application perspective, because this fact, the mean value is very useful in many applications, okay? So that's the diagram. I hope you understood everything. If you have any questions, you can write them down in the comments. In the description of the video, I'm gonna put a link to the MATLAB code and also to the paper, which is open access. Okay, so thank you very much.